Hi everyone, I'm going to introduce minimal sufficient statistic in this video. In the previous videos, we looked at the formal definition of sufficient statistics and two theorems that can be used to show a statistic is indeed sufficient. We've looked at a few examples for sufficient statistics, so one natural question that might come into your mind is sufficient statistic unique? The answer is no, it's not unique. Intuitively, we can come up with two very simple examples. One trivial example will be the statistic Tx equal to x. Since x has all the information about the parameter theta, given T of x, the distribution of x does not depend on theta. The conditional distribution of x in this case is a constant function of theta, which means Tx equal to x is a sufficient statistic. Another trivial example we can come up with: for any sufficient statistic T of x, its one-to-one function Qt of x is also a sufficient statistic for theta. Intuitively, any sufficient statistic contains all the information about the parameter theta, and a one-to-one function of sufficient statistic will not remove any useful information about theta. That's why we say Qtx is also a sufficient statistic. We're looking for a sufficient statistic that is the simplest, which means minimal sufficient statistic is a sufficient statistic that achieves the maximum data reduction. A formal definition is as the following. A sufficient statistic Tx is called a minimal sufficient statistic if for any other sufficient statistic T prime of x, Tx is a function of T prime of x. So how do we interpret this definition? Remember we said we can view x as a sample space, and Tx is the same space as x. However, Tx has a different partition in terms of how the space is divided into. So within x, we have the original data, starting from x1 to xj, xk, all the way to xn. It has the finest partition since all the elements are included in the space of x. And then we apply a transformation on this x using T of x. And by doing this transformation, we achieved another partition of the space. In this space, the value of T of x is indeed T1, T2, T3 to Tm. Since sufficient statistic achieves data reduction, we know that the dimension of Tx is always less than or equal to the dimension of original x. There are many different ways to do partition in the space x. Maximum data reduction is achieved when T of x has the smallest dimension, which means when m is the smallest, then we say we achieve the maximum reduction, and this T of x will be the minimal sufficient statistic. If we compare the size of different T of x, if the size of T prime of x is no less than the size of T of x, then we say T of x is indeed the minimal sufficient statistic. Minimal sufficient statistic can be also defined in other ways. So let's look at this corollary together. Basically, a sufficient T of x is called a minimal sufficient statistic if for any other sufficient statistic T prime of x, T of x is a function of T prime of x. Let's again draw a picture of the sample space of x. When we apply a sufficient statistic T prime of x, we will make a partition in the original x space. Let's say originally in x space we have 8 elements, and T prime of x achieves data reduction, and in the space T prime of x we have fewer dimensions. We have 4 unique elements. And then these 4 elements are T1 prime, T2 prime, all the way to T4 prime. We know T of x is indeed a function of T prime of x. We can write it as Tx equal to G T prime of x. And if we apply this Tx onto T prime of x, we're going to achieve further dimension reduction. Instead of having 4 elements, we actually only have 2 elements. So you can see Tx achieves the maximum data reduction. In the next video, we will look at a theorem that helps you to show when a sufficient statistic is indeed minimal sufficient statistic. Thank you for watching.